Dear colleagues, physico-mechanical and physico-chemical properties of iron ore raw materials loaded into a blast furnace determine the technical and economic indices of its operation. The particle size distribution of agglomerate, the repose angles of the loaded materials, as well as their bulk density, affect the distribution of components of the blast furnace charge along the radius and around the circumference of the furnace top. Therefore, reliable information about these indices makes it possible to effectively regulate the loading of the blast furnace. An analysis of the physico-mechanical characteristics of sinter makes it possible to develop a rational operating mode for a blast furnace. Using of such a mode provides the efficient application of agglomerated iron ore with various physico-mechanical properties and increases the technical and economic indices of smelting. The paper includes data on the physico-mechanical properties of sinter of various origins, including density, bulk, average and true, porosity, open and total, internal and external angles of repose measured on dropping the material down onto a surface from a steel sheet inclined by 40, 60 and 80 degrees to the horizon. Angle of external friction on the steel surface, the strength properties of the sinter in a cold state and after reduction at a temperature of 500 degrees Celsius. For laboratory study, the samples of iron ore sinter having various chemical composition were taken. The chemical composition of the investigated samples of sinter is presented in Table 1. The particle size distribution was determined by sieve analysis. The results of sieve analysis are given in Table 2. The determination of bulk, average, and true density of the sinter was conducted for the sinter samples number 1 to 4. The connected porosity of the sinter was determined by its saturation with water under vacuum. The total porosity was calculated by determining the average and true density. The bulk porosity of the sinter was calculated by bulk and average densities. The results of determining the density and porosity of the sinter are given in Table 3. For the purposes of this study, the angle of repose was determined by the hollow cylinder method. The outer and inner angles of repose of the sinter were determined by dropping it down from a height of 0.5 meters after moving along the surface of the steel sheet inclined at angles of 40 degrees, 60 degrees, and 80 degrees to the horizon and having a length of 1 meter. After the formation of an asymmetric pile, both its angles to the horizon were determined, characterizing external, the angle forming along the direction of movement of particles, and internal, the opposite angle, angles of repose correspondingly. By raising the horizontally installed surface of the steel sheet, with the sinter layer placed on it, the angle of external friction of the sinter on the steel surface was determined as the maximum angle at which the stationary state of the material is maintained. The results of determining the angle of repose, the external and internal angles of repose in operating conditions, and the angle of external friction on the steel surface are given in Table 4. The strength of a suitable sinter, expressed as resistance to impact loads and abrasion, was determined by testing a sample weighing 200 grams in a steel pipe with an internal diameter of 78.5 millimeters and a length of 1 meter, rotating at a speed of 27 rounds per minute for 8 minutes. After testing, the sample was sieved into 3 fractions, plus 5 millimeters, from 0.5 to 5 millimeters, and less than 5 millimeters. The resistance of a suitable sinter to impact was determined by the percentage of the fraction plus 5 millimeter. The destruction of a suitable sinter by the percentage of a fraction from 0.5 to 5 millimeters. Abrasion of a suitable sinter by the percentage of the fraction of less than 5 millimeters. The determination of the hot strength of sinter, or the strength after reduction, was conducted as follows. The samples of sinter were crushed and sieved into a fraction of from 10 to 15 millimeters and placed into an electric tube furnace. Reduction of the sample was carried out in the furnace by isothermal holding at a temperature of 500 degrees Celsius in a stream of pure hydrogen for 1 hour. After cooling the sample in an inert medium, 99.5% nitrogen, a drum strength test was conducted, similar to the determination of the cold strength of sinter. The results of determining the cold and hot strength of the sinter are given in Table 5. The degree of reduction of the sinter tested for evaluation of the hot strength is shown in Table 6. So the conclusions are: the differences in the physico-mechanical properties of the sinter sample number 4 compared with the sinter samples number from 1 to 3 are as follows. Its average density of 3.2 grams per centimeter cubed is higher than the average densities of the sinters number 1, 2, and 3, the values of which are at the level of 3.27, 3.30 grams per centimeter cubed. The true density is increased by 2.9%. The internal angle of repose of 34.6% and external angle of repose of 28.4% are lower than the ones for the other sinter samples. The highest bulk porosity for the samples number 1, 2, 3, and 4, its values are 0.47, 0.47, 0.46, and 0.50 meters cubed per meter cubed, respectively. The reducibility in hydrogen atmosphere at a temperature of 500 degrees Celsius is increased by 1.5% absolute in comparison with the sinter samples number 1, 2, and 3. High strength characteristics in the cold state: impact resistance 92.0%, destruction equals to 5.5%, abrasion equals to 2.5%, and relatively low strength characteristics after low temperature reduction in hydrogen atmosphere. Impact resistance by the fraction plus 5 millimeter, 29.8%, destruction by the fraction from 0.5 to 5 millimeters, 57.58%, abrasion by the fraction of less than 0.5 millimeters equals to 12.36% due to the high reducibility of the material. That's all. Thank you for attention.